Okay, so now I think still under the lecture portion, there are a bunch of files there. I'll show you what they look like right now. They are these demo files, and they are, I'll put them in order, single sample test, two sample tests, unequal variance, paired sample test, and our ubiquitous North Carolina birth data. Okay, so I'm going to start with the simplest of these, a single sample test. It's an SAV file or both an Excel file and a .sav file and SPSS file. I'm going to start with the Excel file. I think I might have opened SPSS first there, but we'll get both of them up here. So I'm going to go, this part, you can assume that this part is going to be demo, and then the next part we're going to work on is going to be a chance for you guys to do this also. Hey, don't forget to mute your microphones, by the way, guys, unless you want to ask me something. Okay, let me see if this opens up. Looks like that one's going to open first. Today, please. There we go. Okay. Let's see if I can't get the Excel file opened also. Okay, here is SPSS. I don't see the data though, unfortunately. Let me open the Excel file. Okay, so this is just a simple number file, right? It could represent anything. I don't, blood pressures, ages, whatever, just a simple set of numbers. There's 9 pieces of information here. Okay, so I want to do a t-test to compare this to a known value. And I'm going to say that known value, mu 0 equals, let me pick out a good number. I'm going to put it in this box here though. I'm going to say that it's equal to, the average is about 10, is equal to 8.5. Okay, I have a population that I know that the mean value for that population is 8.5. I took a sample from another population. I'll call this population 1. Okay, that's population 0. This is population 1. And I want to know whether the mean for 1 is equal to the mean for 2, or in other words, equal to 8.5. Mean for 0. Are those two means equal to one another? So that becomes my null hypothesis. My alternative hypothesis is that mu1 does not equal mu0. 0. Now I can, since I know that mu0 is 8.5, I could just, instead of putting mu0 in here, I could just put in 8.5. So is it equal to 8.5 or not equal to 8.5? Right? Either way is a good way for me to describe the null and alternative hypothesis. Right? This is my null, and this is my alternative hypothesis. So now I have to test this. In order to test this, I have to calculate a t-value. Before I calculate a t-value, I'm going to want to find a t-critical. What is the critical value of t that I need to exceed to be able to reject the null hypothesis and accept the alternative hypothesis? Well, what is that t-critical going to be dependent on? It's going to be dependent on my alpha, and it's going to be dependent on my degrees of freedom. So my alpha is 0.05. My degrees of freedom is, what are my degrees of freedom? 3, 6. Sample size is 9, but my degrees of freedom is equal to 8. So I could go to the table, or I could just do it in SPSS, equals t dot dist dot t2t, I think, parentheses, and it wants to know what the value of, nope, that's not what I want. T dot inverse dot 2t. You and I have trouble remembering these things. Yep, there we go. So I want to know, what is the t value for 0.05 for 8 degrees of freedom? What t value do I use? Well, I have to use the value 2.31. I'm going to use the value. So that's the value of t I need to exceed in order to reject my null hypothesis. That's my t critical. Let me see if I can get it to copy here. Here we go. That's my t critical. So now I have to calculate my t value for the difference between the mean for this population and the mean for this population. So the only thing I know about the mean for this population is my sample. So what is this going to be equal to? T calculated, okay, it's my own terminology, is equal to, it's going to be equal to x bar 1 minus, okay, minus 8.5, right? The mu 0 divided by, and what is it going to be divided by? It's going to be divided by the standard error. And what is the standard error going to be equal to? The standard error is going to be equal to the standard deviation for, for all of these numbers, for my sample, the standard deviation divided by the square root of my sample size, which is 9. Actually, what I'm going to do is I'm just going to put 3 in there just to make it easier for me to work with. See what that comes up. So it comes out to be 0.9781. That's my standard error. So what's my t equal to? My t is equal to 8.5, the x bar minus 8.5. Well, what is x bar? I got to calculate x bar. Let's see what x bar is. X bar 1. Okay. So yeah, x bar.
Professor, I'm so sorry. What the standard error was the standard deviation of the sample size divided by the square root of what?
9. By the square root of 9.
Oh, of the sample. Okay, thank you.
Yep. I'm glad you asked. If I didn't make that clear, I'm glad you asked. Okay, let me get in here. Try and decide why this is not. Let me delete that. I think I'm okay now. Okay, what's the average? Average is equal to the average of all these is equal to 9.8. So now I'm going to do my t calculation. The top part of my my numerator is going to be the difference between x bar 1 minus mu 0, which is 8.5. The bottom part is going to be my standard error. My standard error is going to be equal to, I calculated over here, standard deviation divided by the square root of the sample size. It's going to be equal to that. So my t calculation, my t critical, is going to be equal to the numerator divided by the denominator. And that's going to become a t-score of 1.599. Can I reject my null hypothesis? Well, no, I can't. Why can't I reject my null hypothesis? Because these two values, my mean of my mean, which was, what was my mean again? My mean of 9.9 is not different enough from the value 8.5 I'm comparing it to for me to reject my null hypothesis. It's only 1.42 standard errors away. Has to be at least 2.3 standard errors apart. Now, what if this had been, instead of 8.5, had been 7.5? Let's see what happens now. What happens now is that my t calculated becomes 2.44, and my t critical becomes 2.3, is still 2.30. So now I can reject the null hypothesis. Why? Because they're at least more than 2.3 standard deviations apart. What p-value does that represent? Well, we just took a look at that, didn't we? Equals t dot dist dot two-tailed parentheses, and I'm going to put in the z-score, which was, or t-score, which was that, comma, and degrees of freedom, which was 8, And my p-value is 0.04. It's less than 0.05, as you would predict. Okay, so I just filled in the values in the formulas that we worked with. Excuse me, for the a single sample t-test. I'm going to do the same test in SPSS, I hope. Okay, and I'm going to bring up SPSS, and I'm going to say, I don't know why it didn't open the data. It should be in there. Open data. And it's going to be on the top here, session 8, and it's going to be in demo files, and it's going to be, here it is. There it is. These are the same numbers that we had just a moment ago, right? So now I'm going to go up to Analyze. Now, if I go to the variable view, you'll see that it has this as a numeric, it has it as a nominal variable. I got to change that to a scalar variable. Let it know it's a number, not like a social security number, something like that. I'm gonna go back here. Probably would have worked anyway, but just to be safe, I'm gonna go to Analyze, and what operation am I going to do? I'm going to compare means, right? So it's a single sample test, which means that there's only one sample. I'm going to take the values for the variable x, move them into the test variable, and then I'm going to compare it to a known mean, a test value of 8.5, as we did before. And I'm going to click OK. Our output window is going to come up, and it's going to do the t-test. So what is a t-test? T-test came out to be 1.42, the same thing as we calculated in Excel. The degrees of freedom is 8. The significance, the two-tailed significance, we didn't bother to calculate that when we failed to reject the null hypothesis, came out to be 0.193. And this is also calculates confidence interval, and you'll notice that 0 is inside, 0 difference between the two means is inside this confidence interval. That's another reason we failed to reject the null hypothesis. But really, I'm interested in the t-value, degrees of freedom, and the significance, the p, that's your p-value, your probability of being wrong. Okay, so I'm going to do the same thing. I'm going to repeat this, except I'm going to put in, what did I put in, 7.5? Compare means, one sample t-test, except this time I'm going to change this to 7.5 and see if they're different enough now for me to reject the null hypothesis. What am I doing? I'm comparing the mean for this sample to the mean of another known population, known mean for another population. Click OK, and this time my t-value comes up to be 2.42. My degrees of freedom is 8. My significance is 0.04. There's only a 4% chance we would get this big a difference if the null hypothesis were true, and these two means had come from the same population or have been the same. Okay, so that's how we use Excel or calculator to calculate this. And you can use that. Remember that chart I gave, that table I gave you? I'll pull that up in a second. The table with the different formulas for the different types of tests. I don't even think I bothered showing you the formulas for single sample tests because it's so straightforward. Okay, so are we okay with a single sample test? Okay, we feel pretty confident we can do a single sample test. Let's get a little bit more adventurous now. Okay, and I'm going to go into my folder here, and I am going to, let's see, demos. Now I'm going to go to number 2, is a 2-sample t-test. And you know, I'm going to skip that one. I'm going to go directly to a 2-sample t-test with unequal variances. I'm going to double click that. It's going to open up. Get rid of that thing. So here we're comparing two groups, males and females. And I don't know what that stuff is. I'm going to get rid of it. Okay, and I'm gonna calculate the means for each group. Average for males and the average for females. Okay, whatever this happens to be, the numbers really don't mean anything, right? We could build a story around it, but why bother at this stage? So that's our means, right? That's our mean for females. That's our X bars. Males and X bar females. Okay, So what about our standard deviations? Equals standard deviation for each of the two groups. This is the variability for males, and this is the variability for females. Notice one is like 3 times what the other is, much more variable, right? So you would assume that this was, and this is the 2 standard deviations, right, for each group. Okay, so you would assume that, gee, I'm not going to assume equal variance. It's not. In these two, I'm going to probably just go with unequal variances because they're so different. So that would be a judgment you would make in your head. But even if they were very close, we're going to assume unequal variances because it's going to be, for our purposes, it's going to be a more straightforward test. So now what formulas am I going to use here? Okay, so always, t is going to be equal to x bar 1 minus x bar 2 over the standard error. Okay, so that's going to be pretty universal. So they're going to take the same form whenever we do this stuff. Okay, so what's the complication here? Complication here is on the top is easy. X bar 1 minus x bar 2 is easy to do. Well, what about the bottom? What about the standard error? How do I calculate the standard error? That's where things get a little complicated. It's going to get a little complicated on degrees of freedom possibly as well. So I am going to go in here to my reference files, and there is a thing I gave you. T-test variations. That's the one. And if I go in here, I gave you formulas in this document. This is all on Blackboard, by the way. Formulas for this document that you could use. Actually, no, this is not the document I gave you, is it? Yeah, this will do. This will do for us, right? If you have where sample standard deviations are assumed to be equal, and we want to pool them, we could use this number to get a pooled standard deviation for the two groups. Then we can use that, put it down here, and calculate my t-value. That turns out to be my standard error. If I don't bother to assume that they're equal, I could use the formulas for not assuming standard deviations are equal, and I can use this formula instead. So the bottom, my standard error, is the square root of the standard deviation of one group over its sample size plus the standard deviation of the other group over its sample size, right? So I'm going to go ahead and calculate that. So it's going to be equal. Here's my I'm going to start working on my standard error down here. Get rid of that. So my standard error, right? So first thing I got is I'm going to take my standard deviation here and square it. And then I'm going to divide it by the sample size. Sample size for males is 369. Okay. Okay, and I'm going to do the same thing for females over here. Equals this. Oops, nope. Equals standard deviation times itself squared over sample size, over the sample size, which is 9. That's that one squared. And this now I'm going to take this number, and I am, okay. Actually, I already did that. Okay, so now I'm going to add these two together. And then I'm going to take the square root of that number. Okay, and that's the square root. Notice it's almost 1, so the square root is almost the same thing, coincidentally. Okay, so what did I do there? Let me just bring this back up. I did exactly this. I squared each one of the 2 standard deviations, divided by sample size. I added them together, and then I took the square root of the whole thing. I just did what's underneath this division line, right? So now that's my standard error. So now I can actually calculate my t-value now. My t-value, my t calculated, is going to be equal to the difference between the two means, this mean minus this mean. I'm going to put them in parentheses, divided by the standard error, which I calculated right here. and that's equal to a t calculated of 2.511. Now, can I reject my null hypothesis? Well, in order to reject my null hypothesis, I have to know what the t critical is. The t critical for 0.05, 0, or if you look alpha over 2, 0.025, right? Same thing, right? And how many degrees of freedom? 8 degrees of freedom. Well, what is that value, right? What is that value equal to? Okay, that value is going to be equal to t dot dist t dot inverse dot 2t, I think. And now I am going to put in the probability 0.05 and tell it that I'm working with 0.05 and tell it that I'm working with a degrees of freedom of 8. Oh no, wait a second. Degrees of freedom is not equal to 8. Oh, it is, but I jumped ahead. What are the degrees of freedom equal to here? Well, you got to keep in mind, I have one group has 9 in it, the other group has 9 in it. I have 18 people here total. So my total population, my total sample size, 18. However, if I'm not going to assume equal variances, I have to use this formula for my degrees of freedom. But we already considered that rather than use that formula, you could take a very conservative alternative, which is to use the smaller group for your sample size and subtract 1. So that would be 9 minus 1 would be 8. That's where I got the 8 from. Actually, I forgot, but that's where the 8 comes from. Okay, so what is that going to be? My critical value of t, just like it was before, is going to be 2.31. And since I calculated my t value to be 2.511, I can reject the null hypothesis that the mean mu for males is equal to mu for females. I can reject that and accept the alternative hypothesis that mu for males is not equal to mu for females. And just keep in mind now, your hypothesis, your null hypothesis is that mu for males is equal to mu for females versus mu for males does not equal mu for females, right? We can reject our null hypothesis and accept our alternative hypothesis. Now, if you would, yes, go ahead.
I'm so sorry. Can you do the t critical one more time? I keep getting a different number than what.
Oh, okay, maybe I did it wrong. Okay, equals equals t dot inv inverse dot 2t parentheses, open parentheses. It's asking me for the probability. Since I chose two-tailed, I can put in 0.05 here. I don't have to put in 2.5. I can put in 0.05, comma, and for degrees of freedom, I'm using 8. I'm using the smaller group. The smaller of the two groups are actually the same, 9 minus 1, which gives me 8.
Oh,
and I'm going to hit.
I figured out what I did. I did t dot dis dot instead of t dot in first.
Yeah, so if you had put in 0.025 instead of 0.05, you probably would have gotten the same answer as I got.
Okay, thank you.
This one's the version of it where you can just put in the number for the two-tail test. You don't have to worry, you don't have to use your brain to think of, well, what should I put in here? You can just put in the value, the alpha that you're after, since it's a two-tail test. Okay, so yeah, so that's how I would do that. Now let's do this using SPSS. Yes.
Quick question. In the textbook, it says for the T-calc, point estimate, which I understand is x bar 1 minus x bar 2 minus null. What would that be in this, or in this, if you don't have a null value that you ignore?
I tried. You saw that in the PowerPoint also. What's happening there is that they're saying that the null hypothesis is mu1 mu for males minus mu for females right? Going to take those two minus 0. In other words, is equal to 0 or minus 0, right? Minus 0 minus the difference, whatever mu difference is, equals 0, right? And that difference, the null hypothesis, you're saying that the two of them are equal. So the difference between the result of this is going to be 0 in the null hypothesis, because that's the null hypothesis. You're saying that they're the same, so this has to be 0. So this mu difference has to be basically defined as 0. So it's basically that the difference is equal to 0. So that's kind of what they're doing there. But that saying this is the same thing as saying this. Does that make sense to you?
Right. Yes, perfect. Makes perfect sense, because I wasn't sure if in the problem it says like blood pressure, for example, is 0.33. Do you use 0.33, or if it's equal, you use 0? So that makes sense. Thank
Yeah.
you.
So yeah, no, we do that in statistics just to make sure you're confused, right? We have 18 different ways of nomenclature to do. All right. So let me move on with this and do this in SPSS. Okay, I'm going to take same data in SPSS. If I can find SPSS in this mess here now. Okay, here we go. I'm going to say File, Open, Data. And let's see, 2 sample t-test. Did I take one unequal variance? I think I must have taken unequal variances. Yep. Did I just open Excel again? No, I got the right one. Okay, so here's male and female. Now notice I had to organize the data differently in SPSS. Where before it was a column with male and female, now I have to identify them as 2 different variables. This column has the value, whatever that number represents, and this column has the value for gender, the nominal variable for gender, right? The reason why I need that is because SPSS, unlike Excel, works on the basis of identifying variables and then working with each variable in turn. So I'm just going to go back here to variable view to make sure that they're identified correctly. And yeah, the gender is nominal and the number is scalar, right? And if you click in there, it tells you that 1 equals female, 2 equals male. So I am going to go ahead with my analysis. I'm going to say Analyze Descriptive Statistics. And I'm going to go to, oops, I'm sorry, Compare Means. I'm going to go to Independent Samples t-test. Notice it doesn't say anything about equal unequal variances at this stage. It only says independent samples, which is we're going to get to that point in a moment. Okay, so what is our test variable? Test variable is the one that we're going to find, the one that's going to give us our means. So we're going to move that in there. We're going to take the means of those numbers that are in the column values. But we're going to group them by gender. We're going to split them up. In other words, a grouping variable is kind of a factor. We're going to factor them into 2 groups, males and females. So now, because there could have been that, even today, right now, instead of just male and females, that may no longer be a dichotomous variable. You may have male, female, you may have a transgender, you may have whatever, you may have more than 2 categories for what someone identifies as under gender, right? So you have to tell it, since a t-test only compares 2 groups at a time, you have to tell it which 2 groups are you talking about. There could be more than 2 groups. In this case, you would think a program that costs $1,000, full price, you would think it'd be smart enough to see there's only two values here. I don't need to ask this silly question. It doesn't. So go into define variance. So you have to tell it that the 2 groups within your variable gender are labeled 1 and 2. Could have been you wanted to compare 1 and 3 or 2 and 7 if there were more, if it were ethnicity, could be many different groups in there. And you want to compare just 2 of them. And that's what a t-test just compares 2 of them. So sometimes if you put in 0 and 1, you'll see you get funky results because 0 doesn't exist here. Okay, so I'm going to click OK. Our output window is going to come back up. And we're going to see that it's going to give us some basic statistics there. It's going to tell us the mean for females is 10. The mean for males is 7.56. We know that because we just did that. The standard deviation for the 2 groups is just as we calculated before. It calculates standard errors of the 2 individual groups over here, just for the hell of it. But it actually does a much more complicated analysis down here. So what does it do? Well, now, instead of just assuming equal variances, or assuming unequal variances, or not assuming equal variances, SPSS actually does both tests. It uses both formulas to calculate the t-score. Now, if you might notice, look at this. The t-scores are exactly the same. That's chance. Sometimes it'll be a little bit different. They're almost always going to be very close, but they're not always going to be exactly the same. So if I look here, I see that this top row is the calculations if you assume equal variances. The bottom row is if you assume variances are not assumed to be equal, right? So it actually did this test twice. This first part where it says F in significance, don't let that fool you, that's significance. This is not part of the t-test. There's a little vertical bar here that's kind of hard to see, right? This is Levine's test for the equality of variance. This is a mechanism to test whether the variances are equal or unequal. And the way that this test works, and to be honest with you, you're not going to need to use this for our purposes, but the way that this test works is it just like everything else, it assumes a null and alternative hypothesis. The null hypothesis is that that these have equal variances. Variance for group A equals the variance for group B. The alternative hypothesis is that the variances are not equal. So it calculates a statistic based on these two variances. That's the statistic it calculates, and that's the p-value for that test. The p-value is less than 0.05. What does that tell you about your null hypothesis? It tells you can reject your null hypothesis and take your alternative hypothesis that they're not assumed to be equal and use the bottom row instead of the top row. For our purposes, we're always going to use the bottom row. In general, that's considered a more conservative approach. So that's what we're going to do. We're going to use the bottom row here. But this is not our t-test here. This is all just that test. And in fact, had we looked up here, look at the standard deviations, one's 3 times what the other is, just mentally, we would just guessing, we would probably say they're not equal, right? We would probably want to use this test anyway. So I'm going to use the bottom t-test. And the bottom t-test tells me that the t-value is 2.51. How is that calculated? It takes the average, the difference between the two averages, right? It divides them by the standard error that it calculates, and it compares them with the critical value of t. Now, it's got to calculate the t critical. It's got to calculate the degrees of freedom in order to know what the p-value is going to be. Like what the critical value of t is going to be. And notice that when you do equal variances, it just adds up the two, n1 and n2. 9 and 9 is 18, subtracts 2, makes it 16. When you do the unequal variances, SPSS actually works out that very complicated formula, and that's why you get such an oddball number for the degrees of freedom. So if I go across here and I look at this, the t-values are identical, but the p-value is 0.031 for unequal variances. Okay, so what does this tell me? This tells me that I can reject my null hypothesis. Look how big that t-value is. I'm willing to bet that the t-value, t for 10 degrees of freedom, it's probably something like, I don't know, something like 2.2 or something like that. So it well exceeds that 2.2, right? So you can reject your null hypothesis, but you can also reject your null hypothesis because the real actual probability of getting this extreme a difference between these two means for male and female is really only going to happen 3% of the time, which means that you only have a 3% chance of being wrong if you reject the null hypothesis and say that these samples are not from the same population, right? So it's 0.031. Why do you think this, as I said, is more conservative? So the p-value is higher, right? So why do you think it's the same t-value? Why is it saying 0.031 here and 0.023 here? Anybody want to hazard a guess on that? What do you think? It's right there in front of you. It's in the row to the left of that value, of that p-value, that significance. Look, the degrees of freedom are...
Freedom.
Yeah, I'm sorry, go ahead.
Degree of freedom.
Right, exactly. The degrees of freedom here are less. So it's looking at it as if it's a smaller sample size with less confidence. So you can have less confidence that you should reject your null hypothesis than you would with a larger sample size, even though the t-values come out to be the same. So in our case, if you get anything like this on a test, you're always going to be using the bottom row. Don't worry about it, especially if you have to calculate it by hand. You use the bottom row, and then instead of calculating this degrees of freedom, just going to take the smaller sample size, subtract 1. So we used 8 instead of 10.15, right? That's why our Our p-value was probably a little bit, I think it was 0.04 our p-value, right? It's even a little bit higher than this. Okay, and that's it. That's how we do this test, right? So let's take a look at what our next possibility is. What's the only thing that's remaining that we haven't done yet, that we haven't done in this group yet, right? What kind of test? A paired samples t-test. Okay, so I'm gonna go to here, and I'm gonna go to my demo files, and I have data here for paired samples. Let's open up the Excel.
Professor, I have a question in that.
Yes.
In that, the significance in the first one, the significance for a single tail is present only in the upper row, not in the lower one. But in the two tail, we have both ones present. Why is it so?
I'm sorry. Let's explain that to me again. Hang on a second. Let me get to get to that page first. So I know what we're talking about. No, that's
in
not.
this,
Hang on a
the
second.
significance. Sorry.
Wait. I want to get to that page so I get this right. But go ahead. Yes. What were we going to say?
In this first significance, I suppose, is the single tail one, and the second one is the two-tailed one. Am I right?
In here, no. This is equal variances. So they're both two-tailed, right? Oh, you
They
mean
both are two-tailed.
this significance
Yes,
has
this
nothing
one.
to do with the t-test. This significance has nothing at all to do with the t-test.
So we are to always read the significance, which is after the significance
Right.
after the t-test.
Exactly.
Okay.
This is the one that we're working.
Okay.
This part, can you see that there's a thin line up here, goes all the way to the bottom, right? That's to separate it from the t-test. All this is to help you decide whether to use the top row or the bottom row, right? So that's the only function that this has. Do you use the top row or the bottom row? It has no other impact on what the t-test is, right?
Okay.
So I just did this to explain to you why it's here and what it means.
Okay.
But for our purposes, you can ignore it. Just use the bottom row from now on for this course. Just use the bottom row. Okay?
Okay. Thank you.
Okay. So let me go back to my window here for this. The test I just opened. I should start closing windows here, right? Let me see here. I gotta move this thing out of the way so I can get to Windows. Did that single sample, two sample. I think I closed the window inadvertently. Let me try it again. Okay. Oh, I know what I did. I was going to do it in Excel first. That's why I'm having this problem. This it? Okay, here we go. All right, so now we have 9 subjects here, right? Funny how I keep coming up with 9. See, it's a good number for a square root, right? So I have 9 subjects here. Not 18 subjects. I have 9 subjects. This is subject number 1, subject number 2, subject number 3. Subject number 1 took a placebo for 2 weeks. Maybe it's a blood pressure drug. Took a placebo for 2 weeks. They measured his blood pressure. Then he took the drug for 2 weeks, and then they measured his blood pressure. For this guy, there was no change, right? The difference here is this minus this. Okay, for this person, he took the placebo for 2 weeks, and his blood pressure was this. Then he took the drug for 2 weeks, and his blood pressure was this. The difference was the difference between these two, right? Actually, I can just do this, right? And so on, and so on, and so on. Now, in real life, if you did a study like this, randomly, you would assign it randomly. So this person, number 2, this person, first subject, takes the placebo first, takes the drug second, but the next guy takes the drug first, the placebo second, and you assign that randomly. So you don't have everybody taking one first, the same one first, and the same one second, to remove that as a confounder, right? So really what we're interested in here is the differences. These are the individual differences. So the mean difference, X bar difference, right? What is X bar difference equal to? It's equal to the average for all of these differences. And the average difference turns out to be 1.5, right? Now, let me ask you this. If there was no difference between the placebo and the drug, what would you expect the average difference to be? Well, sometimes you'll get somebody that goes up, sometimes you get somebody that goes down, but on the average, you would expect the differences to cancel out if the drug and the placebo did the same thing, and the average difference to be equal to 0. So therefore, my null and alternative hypothesis are going to be that the difference is equal to 0. And my alternative hypothesis is that the difference is not equal to 0. This is obviously a simplified version of of how you might describe it, because again, you could take x bar 1 minus x bar 2 minus mu 1 minus mu 2, but it's really the same thing. It's going to be the difference is equal to 0, or the difference is not equal to 0. Okay, so now how do I actually calculate this? Well, what have I created here? This is really just a single sample test, except the value that I'm comparing it to, right, the mu difference, the value I'm comparing it to is 0. I want to know whether it's the same as 0 or different from 0. So I am going to find the average difference, which I have already. That's the mean. Okay, I'm going to find the standard deviation. That's equal to standard deviation of the differences, that is. That's equal to this. And then I'm going to find the degrees of freedom. How many degrees of freedom is this? Well, it's only 8 values. It's only 8 different measurements. So the degrees of freedom are equal to 8. Okay, and I think you could probably check that for me. I'm sure that's what it is. It's just 8. Okay, so now I have to calculate what is my T critical going to be.
Professor, I have a question.
Yes,
This is a paired test, right?
that's a paired test. Yeah.
So a paired test and a single sample test, how are they different from each other?
They're exactly the same. I'm not looking at these. I'm not comparing the average for the placebo to the average for the drug. I'm comparing the difference to a known value 0, right?
Okay.
So it's just one column of numbers, the mean for one column of numbers compared to a known value of 0. That makes it basically just another version of a single sample test.
Okay. Understood.
So T critical is going to be equal to, okay, I'm going to, let me see, T critical is going to be equal to T dot INV dot two-tailed, two-tailed parentheses, and 0.05, comma, degrees of freedom is 8. We've done this before. It comes out to 2.31. That's the T value I have to exceed to reject my null hypothesis. So what is my T calculated? T calculated. How calculated? Okay, that's going to be equal to, the difference minus 0, right? Remember that funny thing on the formula on the top? It's going to be 0 and 1. So it's really just the difference, the mean difference, divided by the standard error. Okay, so what's the standard error going to be equal to here? It's going to be equal to the square root. It's going to be equal to the square root. It's going to be equal to the standard deviation divided by the square root of the sample size. And the sample size is 9. So I'm just going to put 3 here again, because I know Excel is going to, something about that format Excel doesn't like. And it comes out to be 1.72. So now my T calculated does not exceed T critical. So as a consequence, I fail to reject the null hypothesis. Right? So what is the p-value here? The p-value is equal to T dot dist dot two-tailed parentheses, and I'm going to put in my z value, which is my t value 172, and my degrees of freedom, which is 8, and it's going to tell me the p-value. It's going to come up. I know it's going to come up bigger than 0.05, because in order for it to be less than 0.05, I would have had to have a t calculated bigger than 2.3, and it comes out to be 12%. There's 12% chance that we would get this big a difference if the null hypothesis were true, right? So that's too big a chance for me to reject it. It has to be less than 5% chance for me to reject the null hypothesis. So that's where we are there. And let's do the same thing now with, let's do the same thing again with SPSS. Okay, and I'm going to find SPSS again. And let's see, SPSS, and our paired samples, SPSS, should be the same data in this file. Okay, now notice this time we're not listing it separately. We're not listing one variable here and another variable here. Each row here represents a subject. So subject number 1 has 2 values, has the value for when they took the placebo and the value for when they took the drug. Unlike before, when we only had a single column there, and we had for the values, and we identified the group it came from. This is the format I need to have it in order to do a paired sample test. So I'm going to go up to Analyze. Again, compare means, except this time, one sample, independent sample, and paired sample. So when paired samples, now notice this, it's asking me which 2 variables I'm going to use as my paired samples. So it's going to be my placebo, and it's going to be my drug. Notice I can't do anything, no OK, the OK is shaded out, until I put in something to compare it to. And so I am going to click OK. And it will run through the test for us, and let's see what it comes up with. And now it comes up with a single line, just like when we did the single sample t-test. And the mean is 1.56, the standard deviation is this, standard error is this, and it does the t-test. And it finds that the t-value is 1.730, and the degrees of freedom are 8, and the significance is 0.122, 12%, right? So since this is not less than 0.05, and since this is not less than the critical value of t that I need to exceed for 8 degrees of freedom, I failed to reject the null hypothesis. I haven't proved that the placebo works to reduce blood pressure more than the control, more than the drug does. The drug doesn't reduce blood pressure more than the placebo does. I can't, keep doing this stuff, and it gets pretty confusing. Okay, so let's pause. Let's pause that right now, and let me give me a chance to questions. Do you have any questions about this? Because what I'm going to do is we're going to take another 10-minute break. If you don't have any questions, or if you do have questions, hit me with them now. Take another 10-minute break. I got to clean this mess up so I can find stuff here again, and then we'll be back together again. So, do you have any questions? So there's nothing you don't know, but you don't need me anymore. I could go away into the sunset. I could go on vacation, and you don't need me to explain this anymore. So everybody's perfectly fine with this. There must be something that you're uncomfortable about. No? You're okay. Okay, you guys are okay for now. Okay, in other words, we'll see. We'll see when we actually have to do it. We'll see how well we know it, which is good, because that's what we're going to do next. I'm going to give you a chance to do it yourself, and we'll see how well you really know it, and that's the best way. And if you're active on Blackboard, you can exchange information go on the forums, and you could talk about this and work these problems out together. I have no problem with you collaborating on Blackboard on the homework, not on the exams, but on the homework. I don't have a problem with it. Try not to just trade answers, right? Try to explain things to each other.